All right, let's continue talking about powder characterization techniques. All right, so where we left off was on my list of 11, I believe. So this is number 6. And so this is X-ray diffraction. And so X-ray diffraction could be really used in 2 different ways. So the main purpose of X-ray diffraction is to identify phases present. And so we can definitely use X-ray diffraction to determine the crystalline structure and phase of a given ceramic powder. Also, in that same way, it could be used to characterize any impurities that may be in the powder. But the other way that I wanted to talk about the use of XRD was to look at what we call the crystallite size of these crystalline particles. So again, it has to be, the limitation here is that we can't do it on amorphous materials. It's only for crystalline materials. But what we see with crystalline materials is that the crystallite size, the smaller and smaller it is, the broader and broader the peak appears. So this plot shows it here. So the higher temperatures, which have the narrower peaks, so the width is narrower, correspond to larger particles. And then as we go down here to much broader peaks, that corresponds to a smaller crystallite size. And so this technique is valid for nanocrystalline size. So very typically only up to about 100 or 200 nanometers. So all the other techniques that we've looked at so far are typically good for micron-based size. This is for much smaller particles. All right, so one distinction I've been making here is I've made a point to say crystallite size and not particle size, because there's a difference. It might be subtle in some cases, but there is a difference. And so the best example I can think of is to kind of look at this scenario here. So let's imagine, and this is just an either TEM or SEM image of a particle. What we kind of see here is that this quote-unquote particle is actually made up of several crystals. So this one here, this one here, this one here, and this one here are all separate single crystals, but they're kind of joined together, right? This is a green boundary here, 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 and here, right? So they're joined together. And so if you were to look at this under a light microscope, you would think that this is one particle. But since we can kind of see the contrast here, we know that it's actually multiple crystals. And so the difference is that in X-ray diffraction, since we're looking at the crystalline structure and we're looking at the spacing between peaks, then it's going to measure the size of individual crystals. And so when we talk about crystallite size, that's going to tell you the size of this particle, or this particle, or this particle, or this crystal, right? Whereas particle size, you would typically measure the overall size of all of this joined together. And so the main difference is that crystallites refer to an individual crystal, so a single crystal orientation, whereas particles may have several, but they might also have one. So if a particle only has one crystal, then the crystallite size is also the particle size. But there can be a distinction if you have this type of scenario. So that's why I'm very specific in saying the crystallite size when looking at these materials. All right, so let's look at how we actually measure this. And we do so with an equation called the shear equation. And so what that does is it measures the diameter of a particle by the wavelength of X-ray diffraction, of X-ray wavelength that we use. It measures the Bragg angle, so the peak location, that's theta. So that's our Bragg angle for that given peak that we're identifying. And then also, most importantly, we're looking at beta. So here, beta is known as the full width at half max, so FWHM. And so this is, as the name implies, the width, the full width at half maximum. So how we get that is if we're looking at one of these peaks. So let's look at the top one here. So let's look at this 25 degrees Celsius. The background is this line right here, and then we have a peak. So the maximum is right here, but it asks for at half the maximum. So basically we would take the difference between the peak and the baseline, so it'd be somewhere around here, and we take the full width. So basically we're gonna find the width of this peak at half the maximum. So that's what. So I always like the distinction full width half max, because it tells you exactly what you're trying to get. But that's what beta is in this case. So the Bragg angle really doesn't change, as you can kind of see from this image, and so that's constant. The wavelength of X-ray tends to be constant for an experiment. And we have this 0.9, which is a constant. This is known as the shape factor. So we're going to use 0.9, but sometimes when you do this in X-ray diffraction software, you may use a slightly different constant based on the machine or the calibration of everything. But 0.9 is a good approximation for us. So using all that, that's all really constant for a peak. And so the only difference then is the width. So if all of these have the same Bragg angle, have the same wavelength, and same constant here, then the only difference in determining the crystallite size, D, is going to be the width. And so that's what we would have to use to calculate this. Okay, so let's kind of run through an example of this. So I put the equation here on the slide again. I've got an image of a single peak, so we're just looking at this one peak. I've given you the wavelength of radiation that we use for this experiment. So this is actual experimental data. So you have kind of the some noise and then a peak that appears for this. And I want you to see if you can estimate what this crystallite size would be based on the equation and based on your measurement of the width. So if you want to go and look at this image in image J, that is perfectly fine. If you want to sort of do it with PowerPoint just to get a rough measure of this, and you can use this as your scale bar, right, to get the width and everything. So use your degrees down here, and then see if you can come up with the diameter, and then we will come back and take a look at what I have. So pause that and see if you can work through that problem, and then come back and we'll see what particle size we get. Okay, so the first thing I want to do is just show you the overall spectrum that this came from. So this was, like I mentioned, platinum nanoparticles, so they're very small, produced in a certain way. You might recognize this from the lab. In the sample report that I gave you, it's basically the same data set. But this is the full spectrum that we have of the data. And so I'm just giving you really that one peak right here to look at. And so from the data that I used software to solve, I got the crystallite size of 7.9. And so we're going to do it manually and see how close we get to that 7.9 number. But here, I want to sort of caution you, with these crystallite size measurements, the accuracy of these numbers is quite low. And so I tend to not give a lot of significant figures because there's quite a bit of error in these measurements. It's really... usually refer to it as an estimate of what the crystallite size is. So that's something to keep in mind. All right, so based on the data that you have, that I gave you from the previous slide, let's take a look and see what we have. So I actually used image J for this. And so I found the peak and then the baseline, and then found the halfway mark. So basically right at this, pretty close to this point. And then I measured the width with image J, and then compared it to the scale bar down here, and then I got a value for the width, so that's beta, in this 2 theta markings as 1.24 degrees. So it was 1.24 degrees wide. That's my full width half max. I've also converted that to radians here. But again, I'm keeping it in terms of 2 theta because that's something that we're measuring here. All right, so the other things that we have in this, the wavelength, I've left that in nanometers. We have the 0.9, so the constant. And then the other part, we have to have the Bragg angle. So there I've got the center location, so I can also use MSJ or some tool to get that. So in terms of 2 theta, I got 67.5. If you got something slightly different, that's okay. But it's actually asking for theta, so I've divided by 2 and got 33.8. And I've also converted that to radians because that's what I had set in for this cosine equation. So if you're using degrees, that's fine. Whatever your calculator is set to, make sure that that's the proper units. But I will want this beta, this full width half max, in terms of radians because my units up here are nanometers, and so I want the units to be in nanometers, not nanometer degrees. So excuse me, that should be in, so basically that should be in radians, but it should be in terms of 2 theta, whereas Bragg angle should be in terms of theta because that's what the equation is asking for. So so if you had some trouble with that, that's perfectly fine. But I did want to reiterate that here. So nanometers, radians here in terms of 2 theta, what you're measuring from the screen. And then this one is theta, not 2 theta. So that's what that should all be. And when I plug that in, I get a diameter of 7.7, which if we go back is really close to that 7.9 that we have. So that's a way we can measure and estimate what this crystallite size number is. Okay, so now let's sort of move on to some other techniques in measuring different than particle size. Excuse me. So the first one is BT. So this is 3 scientists' names, basically, but shortened to just be BET. So what this does is, opposed to all the techniques we've talked about so far, this doesn't necessarily give us particle size. What it actually does is give us surface area. And so obviously surface area will tell us something about the size of the particles, but if we have a lot of pores and irregularities on the surface area can be quite large compared to a very smooth particle. So basically what this technique does is we have a gas such as nitrogen, N2, or krypton, and it's absorbed on the surface of a material at very low temperatures. So we basically take this material to cryogenic temperatures and absorb these materials. So you'll see that all these gas particles have absorbed on the surface of the particle. And it doesn't necessarily just have to be one layer of gas molecules. It can be multiple, as you kind of see here. So what we do after we've absorbed this gas at these low temperatures is we raise the temperature to desorb these gas molecules. And we do this as a function of temperature. And so we have how much gas is desorbed at a given temperature, and so that we can measure it with a pressure. So since this is sort of in vacuum, any gas molecules that come off result in a gas pressure, and this can be measured, and it's going to be proportional to how much of the material surface is. So you can see here that if these gas molecules are desorbed, we're going to get X amount of gas molecules based on the size of the surface. So more surface area, more gas molecules. So we can get that surface area. But it also gives us a lot of other useful information in terms of pore sizes. So you'll see up here that this is a relatively large pore, and this is a relatively small pore. So what we find is that the desorption doesn't happen all at one temperature or one condition. The gas molecules here desorb much easier than they do from this small pore. And so we can use that dependence of temperature to actually look at the varying particle sizes, or sorry, the varying pore sizes in this material. So we can actually use it to determine the distribution of pore sizes that we have. Oh, excuse me. All right, so let's sort of go back and look at what this gives us. So let's imagine we have a relatively non-porous solid, which has, low surface area, doesn't have a lot of pores. And then we have something like this, right? It's a very porous material, has a lot of surface area. So this is going to give us a higher surface area per mass than this material over here. And it's going to give you more pore volume than this material over here. And so we can get that information. So along with just a number of the surface area, we're also going to get this kind of plot up here. And this shows us the distribution of pore diameters with the material. So this is kind of showing us that we have the most frequent pore diameters is about 6 or 7 nanometers. We have some that are smaller, and we have some that are larger, but that's kind of the average size based on this plot. So it kind of tells you based on the volume, the amount of volume, what you have. And so that can tell you information about the pore diameter. So that's very useful information and not necessarily something that you would get from other particle size techniques. Okay, so we've talked a lot about particle size and then just now surface area. We haven't really talked about any compositional techniques yet, other than EDS or something that you can use inside of a electron microscope. Excuse me. So I did want to look at some spectroscopy techniques that we can use. And the first one is flame emission spectroscopy. So this is basically a fancy version of what you might be familiar with as the flame test. So basically you put a small amount of some material in a flame, and based on the ions present, it will change the color of the flame, right? So lithium is this kind of reddish color, sodium is this orange, potassium purple, copper is this green color, indium is this kind of bluish color, lead is this lighter color. This is also the same kind of principle behind firework colors, right? So it's the same idea. But basically, this would allow us to do this in a more controlled manner. We can determine what elements we have present and also get a very precise, accurate method for determining small amounts of these types of elements. So we can get how much, what the composition is of this material. So it's very good for small amounts of these alkali metals. And so it uses the color, but also the concentration. So this is kind of an example. So this is showing you the flame. So this is the flame. So there's basically a flame present, and then you eject a small amount of a liquid. So the liquid is your powder that's been dissolved into a solution. So maybe with an acid or something like that. So it's in solution in a controlled amount. So these are actually standards. So this one has 0 milligrams of calcium per liter. This one has 10 milligrams per liter. This one has 600 milligrams of calcium per liter. So these are standards. So what this shows us is that the flame with no calcium looks like this. And then if you put a little bit of calcium, you've got the sort of orange color, but it's not very intense. And then here at 600, you've got this very intense structure, or very intense flame color. And so these are standards. So what we can do is we can compare our material that's been dissolved in a certain amount of liquid to standards, and we can get the amount of these ions per liter. And so this gives us a really accurate amount, even at the small end, at the low impurity levels, of how much we have in these materials. So this is often a very good way to get things like lithium and other light elements that aren't picked up very well on something like EDS. And so this is a very common technique, flame emission. There's also variations of this. One of them is known as ICP. You can look that up, inductive coupled plasma spectroscopy. And that is a very similar technique to this flame emission spectroscopy, but it gives us concentration, very low amounts of these metal ions.